Okay, so hopefully the n equals 1 step didn't give you too much trouble. You're just going to be plugging in literally 1 for your n. Hopefully you don't have any trouble with that. Just going to do sys, make sure my pins work. Okay, so you're going to basically plug in n equals 1, and this kind of goes without proof. Why is this a true statement? Well, anything to the first power is going to be the thing that you started with, right? So I'm sure there's a name for that rule. But basically, first power just means to not multiply it by itself, right? So that's just cis theta. And 1 times theta, the identity property of multiplication says that that's just theta. So this first part is just obvious, okay? Did everybody write this on their paper? I told you to show that it's true for n equals 1. Okay. Now you're going to assume it's true for n equals k. So this is a little iffy. You're just writing down this rule with a k in it instead of an n, and you're pretending that this is true. Okay, now before you say, well, hold on, I can't assume that. I'm trying to do proof. I'm just making assumptions during proof. Actually, part 2b here, you're going to show that if you update this to k plus 1, the formula still holds true. So you're kind of using it just temporarily, making this assumption. And this is not steps 1, 2, and 3 really. It's really steps 1, and then this is like 2a and 2b. Step 2, the goal is to show that for all k comma k plus 1 pairs, the statement holds consistent. So now you're going to update to k plus 1. How many of you actually tried to update to k plus 1? Okay, so hopefully you wrote sys theta to the k plus 1 equals sys of k plus 1 times theta. Anybody have that? Okay, we just changed our k's to k plus 1s. So the tricky part now is to show that the left side of this and the right side of this are actually the same thing. Okay? So that's kind of the hard step, I guess you could say. So let's pick it up from there. I'll give you a few minutes. If you didn't get this far yet, now you have, but I want to give you some more time to work. Remember, if you have, a to the k plus 1, that's the same thing as a to the k times a to the 1, right? So you could actually split this up into 2 parts. That's what you need to do next. Just like a to the k plus 1 is a to the k times a to the 1. So cis theta to the k plus 1 would be something to the k times something to the 1. So please split that up, and I'll give you a couple more minutes to play around with it. So I'm basically asking you to split it into cis theta to the k times cis theta to the 1. Don't touch the right side, because this is an identity proof. So you're trying to show that the left side and right side are identical. What did you assume back in step 2a? What did you assume back in step 2a? Cis theta to the k was what? This is cis k theta. That was actually our assumption. So we're going to steal that for a moment. That this is cis k theta. We're just stealing that from step 2a. Okay, now here's where it gets interesting. You guys remember what cis means? Cosine theta plus I sine theta, right? So what would cis k theta be? What would it mean? Means what? Cosine what? K theta plus I sine k theta. That's what cis k theta means. And what does cis theta mean? Right. Cosine theta plus I sine theta. So just for a few minutes, we need to sort of unabbreviate so we can properly FOIL this together. So now FOIL this Okay? You're going to find that you have 4 terms. 2 of them are real, and 2 of them are imaginary. Okay? So we're going to do that. I'll pause the video. Okay, so when you multiply firsts together, firsts, what do you get? Well, if you multiply like cos 20 degrees and cos 10 degrees, you can't exactly call that cos squared. You know what I mean? But you could write it as cosine k theta cosine theta. That's firsts. Okay, let's do outers. What's outers? So we got first, outer, inner, last. What's outers? Yeah, it's I. There's definitely an I, and then there's a cos k theta and a sine theta. A sine theta. That's outers. Let's do inners also. So what does inners give us? Yeah, I sine k theta cos theta. And now let's do lasts. What's I times I? Negative, right? And then I have a sine k theta and a sine theta. Sorry, I kind of ran off the board there. Okay, so you see the 2 blues and the 2 reds. Obviously, the 2 reds go together and the 2 blues go together. So let's write reds first. We have cos k theta cosine theta minus sine k theta sine theta. Then we have the imaginaries. Those guys go together. Why don't we take out the I from those 2 blue guys? We have cosine k theta sine theta plus sine k theta cosine theta. So I'm aware that this is kind of a mess. Okay? But do you recognize the red? What is cos minus sine sine? We've seen that before. Cos minus sine sine. Yeah, it's right here. Cos minus sine sine is on your affinity sheet. If cos minus sine sine represents the cosine of the sum of the 2 angles. So what are my 2 angles here in red? K theta and theta, right. So this all collapses down to be simply cosine of k theta plus theta. Okay, now look at the blue. There's an I here, of course. Do you recognize cosine sine plus sine cosine? Where have we seen that before? Yeah, that's the sine sum formula, right? Right there. So this must then be sine of k theta plus theta. I like the, oh, that's a light bulb moment for somebody there. Was that you, Danuk?
Yeah, it's the same.
It's pretty exciting. I mean, what's cosine garbage plus I sine garbage? What's the abbreviated form? Cis garbage. Right. So we actually accomplished our goal. We were trying to show that this was... Oh, I guess we need to factor out a theta here. We're going to pull out a theta, and then there's a k plus 1 there. This is exactly what we were hoping to prove. If you look up a couple lines here of work, we were trying to show that cis theta to the k plus 1 was cis of k plus 1 theta. And down here, we got the left side to work. This really is So that's pretty exciting. And yes, we could put QED here, which means it had to be shown, and we showed it. Or in Hick terminology, it's I done did it. Okay? QED. QED is the formal Latin, and I done did it is the Hick notation. I done did it. Itty. Okay? Any questions on that? So there are a lot of inductive proofs we could do, but I thought this was probably the most valuable one to you because you have unashamedly used this theorem, and now you have reasons to believe it. And it's a cool tie-in with those sine angle sum and cosine angle sum formulas that you learned earlier in the year. So. Okay, so 11.5 is something you've actually studied before entirely. Okay, every bit of 11.5 was in Algebra 2 honors. Okay, but it's an important concept, and it's such a great trick to know. I've used it many times just in my own life, you know, like when I've been taking a test for my master's degree or whatever, I'll bust out and use this thing all the time. Okay? So the first thing we need to talk about is that symbol that you see, NJ. What is NJ? Right here, what is that thing? The way you saw it last year was a little different. It was written as NCR. How many of you recognize NCR? Okay, so let's talk about NCR and what it means. It's a formula, and it's n factorial over r factorial times n minus r factorial. Seems kind of complicated, but it's actually a pretty simple formula to use. Let's talk for just a moment about 5C5. What would 5C5 mean? So you can think of the C actually stands for combinatorial, okay? But you can think of the C as the word choose, okay? So you can see here in my first row of students, Brittany's row, there are 5 students, okay? So let's say that Mr. Shore had 5 students in this row and he wanted to make a group of 5. This question, this symbol means find the number of ways to make a group of 5 using 5 people. Okay, or there are 5 textbooks on a shelf. How many ways are there to take all 5? To choose all 5? Well, if I have 5 people and I plan to pick all 5, there's exactly one distinct group I can create. It is the Brittany, Robin, Angela, my goodness, the June group. Okay? It's that group. There's one group like that. There's no other group like that when you choose 5 from 5. Sorry, June. It's just one of those things. Okay? So 5C5 should turn out to be 1. If you just think about it, there are 5 people there. I want to choose them all. There's only one way I can accomplish that task. So why is 5C5 1? Let's double check it. Well, first you put the first number on top. Then you put the second number on the bottom. And then you put their difference on the bottom. And you basically get this to cancel out. So it's 1 over 0 factorial. And mathematicians decided that they better make 0 factorial 1. So this comes out to 1. Okay? No surprise, in a group of 5, there's one way to pick all 5. Now if I change this to 5C4, it means something a little different. It means that in Brittany's row here with 5 students, I'm only going to pick 4 of them. Okay, now this opens up a can of worms. If I'm going to pick a group of 4 from this group of 5, I'm going to have somebody who feels left out. Or maybe someone who's relieved that they're not in the group. Oh, good, I'm not in that group. I don't have to do it over Mr. Choi's going to do it in the group there. So, but you can think about how many ways can I do this? I can pick Brittany and Robin and Angela and June, and they didn't work out, right? Or I could pick everybody and leave out June, right? Or I could pick everybody and leave out Angela. Or I could pick out everybody except Robin. Or I could pick everybody except Brittany, right? So there are exactly 5 ways for me to leave someone out. And so I expect this to come out to 5. Let's see if it works with the formula. 5 factorial, 4 factorial, and 5 minus 4 factorial. The top is 120, the bottom is 24, the answer is 5, just as I predicted. 5. There are 5 ways to select a group of 4. Let's say you want to talk about 5C3. 5C3 would mean I've got Brittany's row and I'm only planning on choosing 3 of them for some reason. And so let's actually calculate it first and we'll talk about what it means. We're going to do a 5 here and a 3 here and a difference. It's a little more complicated. The top is 120. It means 5 times 4 times 3 times 2 times 1. The bottom is 3 times 2 times 1 times 2 times 1. So this comes out to 120 over 12, or you could say 10. Okay, so it's getting kind of complicated now because I've got 5 people, but I want to pick 3. So, I could pick the first 3, or the first and second and the fourth student, or the first and second and the fifth student, or I could pick, I could just pick the second, third, fourth. There's actually 10 possible groups that can be created here. It's getting more complicated, right? Okay, next would be 5C2. 5C2 has a 5 and a 2, and then a difference, factorialized. But this is interesting. This is the exact same problem we just did. Look at that. Look at that. This one says 5 and then 3 and then 2. This one says 5 and then 2 and then 3. It's the same exact problem. Does that mean that in this group of 5 students, there are the same number of ways for me to pick pairs as triplets? That's exactly what it means. Okay? So there are 10 ways for me to select 3 of you, but there's also 10 ways for me to select 2 of you. That's interesting to me. Okay? Maybe you thought these numbers would just keep getting bigger forever, but that's not what happened. Okay, now let's go on to the next case, 5C1. 5C1. What does it mean? 5 people. I choose 1 person. That happens all the time. A teacher looks at a row of 5 students and calls on one of them. How many ways are there for me to call on 1 student from a group of 5? 5, naturally. There are 5 ways for me to select one of you. You can see how this is tied into probability. You have to learn to count first, though. You can't do probability until you can count. If you don't know the number of options, you can't find the number of desired options divided by the number of options. So this should also come out to 5. It also mathematically is the same problem as the second one we did up here, except instead of 5, 4, 1, it's 5, 1, 4, but that's the same thing, right? So this comes out to 5. And the last scenario would be 5, choose 0. 5, 5, 0, and 5 minus 0. This comes out to 1. In other words, if I should decide that I wish to call on nobody from this group of 5 students, and I don't want to choose anyone, there's one way I can do that. Stand here and keep my mouth shut. Okay? So, notice the numbers are very interesting. It goes 1, 5, 10, 10, 5, 1. You think it's a coincidence that this is a palindrome? It's not a coincidence at all. Okay? Not a coincidence. Whenever you run through the possible calculations for, 5C something, you're going to find palindromic answers like this. Okay? So now that we're comfortable with the formula, we can try these down here. And just know that this year they don't write NCR anymore. They write parentheses NJ. So I don't know why they switched notations on us, but it really just means NCJ, which really just means NCR. Okay? So don't let that throw you off too much. Let's go to the problem set right here. If you want to find 3, 1, you would just do 3, 1, and 2. And work it out. So that's 6 over 1 times 2, which is 3. Part B is 4, 2. 4, 2. So it's 4, 2, and 4 minus 2. So this gives you 24 on top, and 2 times 2 is 4, so this is 6. The next one is 8, 7, so it's 8 and 7 and 1. Now 8 factorial is a big number. I honestly don't even know it. It's in the 40,000s something. But I might not need it anyway, because if it means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and there's a 7 factorial down here, then there's also a 7, 6, 5, 4, 3, 2, 1 down here, you see. Most of it cancels anyway. So the answer is simply 8. So this happens a lot. A lot of the times you'll see stuff cancels out. Okay? So just look for survivors. Those form your answer. Also, notice that nothing's coming out to a fractional answer. Like I'm not getting 8/3 or something like that. Why is that? That's right. You can't have 8/3 ways of doing something. You're going to have a whole number of ways of doing something, always. So that means you can never have j being bigger than n. It's like saying I've got a group of 5. How many ways are there to pick 6 people? Doesn't make any sense. So always keep your j's less than or equal to your n's. And keep your j's positive, because you don't want to say, there's 5 people. How many ways are there to choose -4 of them? That makes no sense either. So j is positive, j is less than n or equal to n at most. D here, 65 and 15. So this is getting gnarly, and we feel like we need a calculator, right? Well, the factorial button is on the calculator, but it's probably not the button you want to go to. You want to go straight to the NCR button. So let me show you where that is again, in case you haven't used it in a while. Turn on your calculator, and you're going to type 65 catalog, and it's down under the ends. So I have to press the log key to jump to the ends quickly. But 65 NCR and then 15. The number's so big the calculator can't display it anyway. Probably should use like Wolfram Alpha or something if you want to see the whole number in all of its glory, because it's a bigger screen and it will actually write the whole thing for you. But this was just a couple digits too long to fit on that little piece of plastic called an LCD screen. Okay, so anyway, I'm not going to write that down, but it's big. All right, let's go to, so that was under catalog and ends. Does anyone have a TI-89? Okay, so if you have TI-89, then you would actually type it like this. First go to the catalog, and you'll see NCR, and then type 65, 15, Robin. Who else has the TI-89? Just Robin. And I don't know where it is in the Casio Genie, so you just have to play around with it. It's probably under numbers and probability. Yeah, math, numbers, and then probability. Or if there's a catalog, look in there. Okay, let's go to the next page. There are some formulas at the bottom, but they're very, very optional. Very, very optional. So, I want to show you something. A minute ago, we were talking about Brittany's row, and we saw that there was 1 way to choose 5, and 5 ways to choose 4, and 10 ways to choose 3 people, 10 ways to choose 2 people. If I was choosing one person, there are 5 ways. If I'm choosing nobody, there's 1 way. And we saw the numbers form a palindrome, 1, 5, 10, 10, 5, 1. So Pascal noticed this and actually created a triangle based on this idea. Okay, you've seen this before, Pascal's triangle. What you're actually looking at, you might not have realized it before, is this is 0, C0. The top here is 0, C0. How many ways are there to choose nothing from a group of nobodies? Well, 1. Don't do anything. Okay? How many? The next row is 1, C0. I shouldn't say nobodies. I meant a group of is nothing. Nobody's a nobody. That's an oxymoron. Okay. The next row represents 1C0 and 1C1. It means you have a group of 1, you decide not to pick anyone. Okay, there's one way to do that. Or you have a group of 1 and you decide you want to pick a person. 1. Those are both 1s. So this whole top part is just 1, 1, 1. Then the next row is 2C0, 2C1, and 2C2. A group of 2 people. I decide I don't want to pick anyone. There's one way to do that. I decide in a group of 2 people, I'd like to choose somebody. There's 2 ways to do that. Or there's a group of 2 people and I decide I want to pick 2 people. Well, you got one way to do it. It's a pair of people standing there. You need a pair of people. So hopefully that's scrutiny. Next row is, 3C0, 3C1, 3C2, 3C3. And this is all down at the bottom too. I just can't see it from the screen. Sorry, it's at 0 always, and then it goes 1, 2, 3. You got a group of 3, you choose nobody, there's one way. You got a group of 3, you choose a person, there's 3 ways to do that. You got a group of 3 people, you want to pick pairs, there's 3 pairs possible. And if there's 3 people, you want to pick 3 people, there's one way to do that. And this last row represents, of course, if there's a group of 4, the various ways of picking groups with size 0 through 4. So this is 4C0, 4C1, 4C2, 4C3, 4C4. Okay, now most people draw this triangle. They don't even realize that these are combinatorials. So most people know how to construct the next row without knowing this fact in blue. So you guys remember how to construct the next row by looking at the 1, 4, 6, 4, 1? You add them, right? So you add any two, first you start with a 1, and you're going to end with a 1. That never changes. But to get the intermediate numbers, you basically add these two together. So that gives you what? 5. Then you add these two together, and that gives you 10, right? And you add these two together, and you get 10. And you add these two together, and you get 5. You've probably seen a teacher do that before, even as early as 7th grade. But see these numbers? 1, 5, 10, 10, 5, 1. Those are the same numbers we calculated with Brittany's row a few minutes ago. Those are 5C0 through 5C5. Right? Notice that every row of Pascal's triangle are palindromic. Right? You can read it forwards or backwards, they're the same. Okay? All right. So which is better, to know the black or to know the blue? Probably better to know the blue, because if you need to find the 15th number in the 65th row, you're not going to want to write the first 64 rows. You don't want to keep crunching these together to get the next row. Just look, you want the 15th number in the 65th row, do 65C14. That's actually the 15th number. 65C14 is the 15th number in that 65 row. So don't forget about that top row there. Okay, here's the cool tie-in though. Watch this. You guys know that when you have anything to the 0 power, that's always 1, right? That includes expressions. Look, x plus a to the 0 is of course 1, right? No surprise there. X plus a to the first is what? It's just x plus a, right? X plus a to the first is of course x plus a. And x plus a squared, you know the FOIL for that. You've probably memorized that. It's x squared plus 2ax plus a squared. You should know that. Maybe you didn't know the FOIL for x plus a cubed. But look at the coefficients here. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Interesting. 1, 4, 6, 4, 1. Wait a minute. So are we saying that when you find the nth power of a polynomial, a binomial, it gives us coefficients that match Pascal's triangle? Yes. That's a theorem. It's been proven, and that is very important to us. So I would like you now to see if you can construct x plus a to the 5th, just sort of following this pattern, and the fact that we have the red numbers right here. So go ahead and do that real quick. And then I've got to jump in quickly and do my examples. We want to see if we can find x plus a to the 5th. We'll just put it right here. You can be sure there's a 1, 5, 10, 10, 5, 1. But I'm hoping you can also figure out where the x's and a's go. Okay? Okay, so notice it's going to have an x to the 5th, of course. What's going to come next? ax to the fourth, followed by what? A squared x cubed, followed by a cubed x squared, and then a to the fourth x, and lastly a to the fifth. Notice that as x, when you first start out, right, x has power 5 and a doesn't exist. But then on the next term, x loses a power, but a gains a power. And then on the next term, x loses another power, but a gains another power. And so there's kind of a balance of power shift here. And in the end, a wins and has all the power, and x is gone. Right? So just think of it that way. But this can also be written in a sigma form, because it's a sum. It's something plus something plus something plus something. By the way, how many terms do we have when we completed this x plus a to the fifth problem? How many terms were in the answer? That's important. 6, right. And that's consistent. When you look at any of these, the power is always 1 less than the number of terms you got. So you're always going to have n plus 1 terms when you do an nth power. That's important. Okay, let's go on here. So don't be intimidated by this, okay? It's awful. It looks awful, but let me explain it to you real quick. This is exactly what you just wrote, okay? It looks very intimidating. But you see these right here in yellow, right here. These are just your Pascal numbers. These are just your Pascal numbers. Those are your, your 1, 5, 10, 10, 5, 1. You just steal it from the triangle. Or if you're too deep into the triangle, you just use NC, whatever, to get it. Okay? So those are just the coefficients. Notice the x starts out with all the power, there's no a. Then on the next term, x loses the power and a gains 1. And then x has 2 powers lost, but a is squared now, see? So this is exactly what we just wrote. It's just all symbolic, and there's no value of n that's expressed. It's just sort of the generic form. And then let's look at the sigma. That thing looks really scary, but it isn't scary. It's the same thing. It's just saying, look, you're going to let your j range from 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8 until you reach n. And that will represent the yellow coefficients. While a is gaining powers, and it always has the jth power, so if you're on the third term, it's got the third power. If you're on the fourth term, it's got the fourth power. The x is always losing powers and has the rest of the n powers. So notice that n minus j plus j is n. In other words, when you add a to the first and x to the n minus 1, you get a total power of n. It's like on the previous problem, we had a squared and x cubed. That adds up to 5 powers, right? 5 degrees. You have a to the fourth, but x is to the first. So that's 5 powers. Okay? So don't be too intimidated by that. Let's try this one here. We know that the coefficients are 1, 5, 10, 10, 5, 1. How do I know that? N is 5. I stole it from the Pascal's triangle. Then we have an x to the fifth, x to the fourth, x to the third, x to the second, x, and then nothing at the end. Now this problem doesn't have an a, but it has a 2. So I guess this will just be sort of like our a. The first term doesn't get one. The second term does. It gets a 2 to the first. The third term gets a 2 squared. Then we have a 2 cubed, a 2 to the fourth, and lastly, a 2 to the fifth. So the last term should read 1 and then 2 to the fifth. And you can put your pluses in because it's a sigma. Okay? I'll let you clean that up. Let's look at example 3. Notice this one doesn't have an x, nor does it have an a. It has a 2y, and it has a negative 3 instead of an x and an a. So you're just going to play the same game. This time it's fourth power. So you're going to have 1, 4, 6, 4, 1. I just stole those from the Pascal's row that has 5 terms in it. So remember, when n is 4, you got 5 terms there. Okay, instead of having x to the 5th, it'll be a 2y to the 5th, of course in parentheses, right? Then there will be a 2y to the 4th, and a 2y cubed, and a 2y squared, and I don't know why I'm doing 5th power, sorry. I meant to do 4, 3, 2, 1 for my powers here. 4, 3, 2, 1. And the last term doesn't get a 2y. Sorry, last term. It's okay. I get all the 3's. Okay, we'll give you all the 3's. The 3's, there's 4 of them at the end. And then it goes 3, 2, 1. The first term doesn't get any 3's. Okay, so you can put in your pluses here. Oh, they were technically negative 3's, weren't they? Got to be careful about that. These are all negative 3's. You can see the parentheses are pretty important, aren't they? So for that one, I'm going to actually write out my expanded solution. And where did I put it? Here it is. Here's what I got. After all is said and done, the first term is positive 16y to the 4th. The next term is minus 96y cubed. The next term is positive again, 216y squared, followed by minus 216y plus 81. Notice that the signs alternate, okay? And it no longer looks like a palindrome. That's because of those 3's and 2's. It's only a palindrome when you first steal it from the Pascal triangle. So listen, there's one more example, 2 more examples that I'm going to record, and then I expect you to watch those. Okay, if you don't watch them, you're not going to do it. So I'm not teaching it tomorrow. We'll do Q&A over 11:4 tomorrow. Okay, but I'll send you the video link this afternoon. Okay, so the sigma form that we learned or saw just a minute ago said this basically. Said that as I wrote that wrong. As j goes from 0 to n of ncj, the x will have an n minus j power and the a will have a j power. So you can kind of just memorize this. I suggest you do. It makes problems like this one much easier. So on this problem, n is 10. You can see that. And so this is going to be sigma j equals 0 to 10, and then it's j10, and then it's x to the 10 minus j, and then it's a to the j. And you'll notice that this problem doesn't have any x's in it. So by x, what we really mean is this 2y. See, that's your x. So you're going to substitute that in right here. And there's also no a in this problem. It's really a 3. So that's going to get substituted in. That 3 is going to get substituted in right there. Okay? Okay, so try to color code it there for you. So let's write this for our problem. Something. So this is j equals 0 to 10. It's 10j. This is a 2y to the 10 minus j. And this is a 3 to the j. So our goal is to have something that has y to the 8th in it. Y to the 8th. So how are you going to have a y to the 8th? That's going to happen when j is 2, you see. When j is 2, you're going to have a y to the 8th. So now that I know j is 2, I can pick out the term where j is 2. It's going to be 10, 2, 2y to the 10 minus 2 times 3 to the 2. And I worked this out earlier. I typed 10c2 on my calculator. I've got a 2 to the 8th here. I've got a 3 squared, which is just 9. And there's a y to the 8th. And they just want the coefficient. So the coefficient would be this part. And I typed it into the calculator to get 103,680. And that's my final answer.